In the 1930s, the LZ-129 Hindenburg was the largest aircraft ever constructed. It measured 804 feet, long enough to line up 3 Boeing 747s nose to tail. While its legacy is defined by its destruction, focusing only on the fire ignores the complex structural engineering that made the ship possible. The airship was actually compromised before the first rivets were set, forced to operate under a specific geopolitical handicap. That constraint was the United States Helium Control Act of 1925. This legislation classified helium as a strategic resource and effectively banned its export. Because the United States controlled nearly all of the world's supply, Germany was denied access to the gas. This political embargo forced the Zeppelin company to utilize hydrogen, the only other gas capable of lifting the ship, but one that was notoriously flammable. Designers were forced to scrap their original plans for the LZ-128. They moved instead to the much larger LZ-129, a ship redesigned from the ground up to accommodate the physics of hydrogen. Hydrogen has a density of roughly 0.09 grams per liter, 1/14 that of air. This provides significantly more lifting force per cubic meter than helium. Across the ship's 7 million cubic feet, this extra lift allowed a payload capacity far exceeding earlier helium designs. Engineers secured the highest lifting capacity of any aircraft to date, but the cost was a reliance on a highly combustible fuel. They utilized this surplus lift to push the limits of internal design, dedicating the extra weight allowance to passenger amenities. These accommodations transformed the Hindenburg into a flying luxury hotel, featuring a full dining room, a pressurized passenger lounge, and heated cabins. The geopolitical ban on helium forced a move to hydrogen, and the unique properties of that gas provided the exact lift required to achieve this level of airborne luxury. This elevation blueprint shows the macro structure of the LZ-129, spanning over 800 feet. The skeleton featured a rigid duralumin framework with 15 main rings and 16 gas cells. Unlike older ships, the Hindenburg's decks were integrated directly into the lower section of the hull. This cutaway detail shows A deck, the upper level of the passenger quarters, where the sleeping and dining areas were located. To minimize weight, engineers used unconventional materials. The cabin walls were made of thin foam layers covered in lightweight fabric. Designer Fritz August Brewhaus created custom furniture for the ship using lightweight tubular aluminum. The weight-saving measures were so extreme that even the lounge's baby grand piano was manufactured from duralumin, weighing just 356 pounds. Every interior element was calculated against the lift capacity of the gas cells, resulting in a ship that balanced heavy luxury with strict weight limitations. On B deck sat the most high-risk area of the ship, the smoking room. Allowing passengers to light up cigarettes directly below millions of cubic feet of hydrogen required a complete engineering workaround. To manage the risk, the room was kept at a higher than ambient air pressure. Clean air was continuously pumped in, creating a positive pressure that prevented leaking hydrogen from entering. This seal was maintained by a strict double-door airlock system. A dedicated bartender monitored this airlock at all times, ensuring that no open flames ever left the pressurized zone. The existence of this room proves the engineers were fully aware of the hydrogen threat and designed deliberate, physical systems to master it. On May 6, 1937, the Hindenburg arrived at Lakehurst, New Jersey, following a thunderstorm that had left the atmosphere highly charged. Despite common descriptions, the Hindenburg did not explode. It was a rapid deflagration. As this photograph captures, the ship was consumed from stern to bow in approximately 34 seconds. By reviewing the German Investigation Commission's findings, we can trace the structural failure that began the sequence. The primary catalyst was likely a snapped tension wire inside the hull, possibly caused by a sharp turn during the landing approach. This wire slashed a rear gas cell, causing hydrogen to leak and mix with air near the ship's outer skin. This created a volume of highly combustible gas in the aft section, needing only an ignition source to trigger the burn. The ignition came from the stormy conditions outside. The airship had just traveled through a highly charged atmospheric gradient. As the crew prepared to dock, they dropped landing lines to the ground handlers below. These lines were wet from the rain, and once they touched the earth, they instantly grounded the airship's duralumin framework. This created a massive electrostatic potential difference. The metal frame was now at ground potential, while the outer fabric skin remained charged. A spark, a brush discharge, arced between the charged skin and the grounded frame, finding the leaking hydrogen and igniting the aft section. Forensic data dismisses theories of sabotage or planted bombs or flammable exterior paint. The Hindenburg was destroyed by the laws of electrical physics acting on a structurally damaged gas cell. The fire lasted less than a minute, but the imagery changed the course of aviation. Journalist Herbert Morrison's agonizing "Oh, the Humanity" broadcast was distributed worldwide, making the disaster one of the first truly viral news events. This visceral documentation permanently ended public confidence in rigid passenger airships. The industry shifted rapidly to heavier-than-air, fixed-wing planes, a technology that would be advanced further by the requirements of World War II. In 1946 alone, 58 new commercial airlines were founded, rushing to fill the market gap left by the grounded Zeppelins. The 34-second deflagration ended commercial higher-than-air travel, acting as a highly publicized catalyst for the fixed-wing airline networks we use today.